Hi everyone. Today I want to share with you a workflow that I hope you will find interesting. In this workflow, we're going to move from sketchy lines, just simply like a wireframe model, into perhaps a solid model. So let me explain that to you for a sec. So assume that that's the model that you have. Somebody has given you this file and it does not include surfaces or solids, it just includes lines. And the lines are not very clean, they kind of overshoot a little bit, as you can see here. And then the question becomes, how do you create a solid using Dynamo and Topologic without having to do it manually and kind of trace over all the edges? So the idea is to move from this kind of model to this kind of clean and solid 3D model. So let me show you some of the nodes that I created. All the custom nodes that I created are written in Python, and they have been uploaded to the website topologic.app. So please download from there. So let's get started. Sorry, the mouse is a bit sticky today. So let's start with Dynamo. Okay, so we'll start a new definition and we'll open a new file path. And let's go ahead, find out where it is. It's on the desktop. It's called Sketchy wire.brep. And we can say by imported brep. So this is a topology node. And now we have a wire. So let's go ahead and visualize this. So we say topology.geometry. And there it is. As you can see, it's just lines and they are overshooting as well. All right, so how do we actually get the faces? A wire is basically a graph, right? So you can apply graph theory. And if you Google graph theory online, and you in particular you Google for cycles, graph cycles, you will find out algorithms and methods of how to kind of deduce or find or calculate the cycles within a graph. And a wire, as I said, is a graph. The problem here is that this kind of problem is what they call exponential or NP-complete, in the sense that you can find a lot of cycles. You know, this type of graph, if you can trace from every point a cycle of edges that comes back to that point, there could be an exponentially high number of cycles. So the way I have gone around it is that I ask the user to specify the maximum number of edges that he or she wishes to see in a cycle. So you can take a look at this model and you can kind of immediately see that there aren't any faces with more than 6 edges. So you can then limit the search to only faces that have 6 edges, and then it will speed it up. It will actually become quite fast. So as I said, these custom nodes are already on the website from topology.app//learning. So the first one we're going to use is called wire cycles. Wire cycles. And oh, right, because I'm calling it from this list here. That's not what we want. We want this one. But before I do that, let me go ahead and do a code block and put the number 6 in it for 6 edges. And really what we should feed it is a wire, not a list. So immediately it came back with 17 wires. So now, why is it 17 wires? If you probably count them, they're probably not 17 wires. The reason is there are cycles perhaps that go through the object and they are still, there's still 6 edges, but they might not be what you on the outside of the solid. So what we can do here is we can figure out which of these wires is planar. Like we can find planar surfaces in it. So in order to do that, I wrote another custom node. It's called R coplanar, and it works with vertices. So you give it a list of vertices, and it tells you within a tolerance whether they are coplanar. So from these wires, we can do topology.vertices. So we can get the vertices here. And of course, it's a nested list. And what we can do then is feed it to this one. And we get a, let's act on the level 2, obviously. And now we get a list of 17 true or false. So we can use that as a Boolean mask to filter the original list. So we can say filter by Boolean mask here, and we're going to feed it this mask, and we're going to get the original list of cycles. And let's do a watch in order to find how many do we have. So now we have 9, and if we count them, probably, if we can say 1 here, 2, 3, 4, 5, 6, 7, 8, and this terrace here is 9. So I think we got the correct wires. So from here, it's a very simple path. We can say face by wires, if this would cooperate. So let's go ahead. Today, the typing is not very good. Here we go. Face by wire. So now we have 9 faces. And now we can simply do a cell by faces. And we have our cell. So let's go ahead and visualize the cell by calling topology.geometry. And there it is. I mean, it feels very simple, but it's really impressive, I believe, in my humble opinion, because it went from just lines to something that is now volumetric and a solid. So let's go ahead and try a different example just to exercise it a little bit. This will take a little bit longer than this one. Obviously, these are few faces here. So what I'm going to do is I'm going to freeze this one here, and I will change the brep file to be a sketchy cone, just to show you what that looks like. So this is the cone. It looks like this. And we are hoping to create kind of a cone with a hole in the middle, right? From this kind of solid. But again, all these lines are extended. You can see it here, but they're also extended at the bottom. I should have deleted that first solid. But let's go ahead and unfreeze this and let it work. And as I said, it will take a little bit longer. Oh, actually, before I let it work, I know, because this is a mesh, that I'm only interested in faces that have 3 edges. So I can reduce this number so that it can go a little bit faster from 6 to 3 and say these are the maximum number of vertices that I'm interested in. So I will unfreeze this. And now it started running. We'll just wait for it. Okay, it's done. So, oops, just trying to get my cursor back. So I will hide these lines, and you can see the end result, a clean solid. And if you look at the actual geometry, we have here a cell and we have here a solid. I hope you enjoyed it. Thanks again.